Okay, so as mentioned previously, the main reason behind the violation of superposition or homogeneity or both of these principles that results in a nonlinear system or turning the linear system into a nonlinear system is the feedback loop. And we have different types of feedback loops. Positive feedback loops are the one that usually contribute to the nonlinearity if it is exponentially increasing. If it is decreasing, then usually we have a negative feedback loop. Now, uh, a simple model to show what feedback loop is. In this case, you can see we have two players, the number of or the population of foxes shown in brown on the right, and the population of rabbits on the left shown in red. And then we have a positive feedback loop on top and negative feedback loop in the bottom, meaning that the relationship between fox and rabbits, or the impact of fox population changes on rabbit, is inverse. That's why this is a negative feedback loop. And the impact of rabbit population changes on foxes is direct. That's why this one is shown in positive. So basically, this is how it works. If rabbit population decreases, that decrease will result in fox population decrease. If rabbit population increases, that increase results in fox population increase. So basically, when we have more rabbits, there's more food for foxes, so fox population grow, and as a result of that growth in fox population, more rabbits are being hunted, which results in decline in the rabbits population. As a result of this decline in rabbit population, food decreases for the foxes, and fox population declines as well. Because of the fox population declining, there's no more hunting, and as a result, rabbit population increases, and this feedback loop continues. Now, the thing is, again, this is a very simplistic, as in reality, we have many other food options for foxes and rabbits, and reality is much more complex. Just to show you how these feedback loops work, I have this very simple model here. Now, um, there are different names for these two feedback loops, and I prefer to use those instead of negative and positive, because it seems that negative feedback loop has a negative impact on the system. In fact, in reality, that's most of the time opposite. The one that usually have a, not always, but usually have a negative loop, a negative impact on the system, is the positive loop. And these are the reasons. Look at the other names we have. For the negative feedback loop, we have balancing loop, self-correcting loop, regulatory loop, and stabilizing loop. These are all other possible names for the negative feedback loop. And in fact, negative feedback loop is the one that tries to keep the system in equilibrium, in the point of attraction. But on the other hand, positive feedback loop results in phase transition in systems, and it is called reinforcing, amplifying, destabilizing. These are the names that we usually use for the positive feedback loop, because it takes the system to the state of far away from equilibrium. So it's basically resulting in uh, uh, phase transition. The example we used about the ice cube becoming water, liquid water, and liquid water becoming gas or steam is the same thing. Because of the increasing the energy level, thermal energy, the state, the phase of the solid to the liquid happens. Change in the phase happens because of the positive feedback loop that is created as a result of that thermal energy. This is the climate change model. It's a very simple model to understand. Let me zoom in and introduce this simulation to you guys first. So let's quickly set up. This is the Earth's environment we have. This blue region is our atmosphere. This black area is the space. This is the Earth. And then this is the basically the layer, the outer layer of the Earth. This is shown in green. It can be greenery or whatever it is. And then on this side, we have the temperature monitor that you are going to see the temperature. And we have the global temperature shown in the line plot here. We can add CO2, which is the greenhouse gas, and we can also add cloud to the model. And the model has two parameters, basically very simple model: sunlight and the albedo, which is the rate that the sunlight is being absorbed by the Earth. Now, I want to start this model very slowly, so you can still, this is fast. Okay. So these yellow turtles or agents are the sunrise that is coming with the intensity of 1, which is the actual, this is the actual amount of the sunlight we are receiving. That's if you want to have that, you should set this to 1. And then part of these turn to thermal energy in Earth, turn to these dots, red dots, which are the absorbed amount of the thermal energy that we receive from sun. Some of these thermal energies escape in form of infrared. These red ones are the infrareds. And if we add basically CO2, these green water drops, these can stop these basically infrareds from escaping Earth. So basically adding CO2 or increasing greenhouses increases the temperature of the Earth, because if one of these red arrows, these red agents, which are infrareds, if one of them hit these CO2s, as this one did, they go down, go back to the Earth, and that's how the temperature increases. On the other hand, if we add clouds, clouds can result in reflecting the sunlight, rays back to the space, and basically reduce the temperature as a result of that. Again, this is not a real model. In reality, clouds also can have negative impact. It is not always cooling down effect. It can be the opposite. So this is not really an accurate model, but it is good enough to show those impact of the feedbacks. So let's watch this one now. So this come up, and that's how it exited. So now the thing is, again, the albedo for the Earth currently is on average 0.6, but it depends where we are talking about. In the poles and in the winter time, when the ground is white and it's covered with the snow and ice, this can be very high, close to 90 something. On the areas that we don't have any greenery coverage, like deserts and dark soils, this can even be much less than 0.6. To start with, let's say we are starting in an ice age with a 0.96 albedo and the sunrise of 1. I'm not going to touch that. Let's set up the model and then add bunch of clouds to the atmosphere. Okay, and start running this model. So as you can see, the sunrise is coming down. Not all of them are passing the clouds. Mostly they are returning, and the very few hitting ground is also reflecting because of the icy nature of it, but gradually this very few ones that are hitting are going to cause some of this ice to be melted down, and that way some of these thermal energies are going to be increased. As a result of that increase, we are going to lose some clouds. Let's say this is the clouds that we are losing, and as a result of that cloud loss, more sunlight can reach to the ground, and then this thermal energy is also increasing, so more ice is going to be melted down. So it's going to be easier to absorb more of that. And then this atmosphere is becoming warmer and warmer, is going to contribute it by CO2 gases being added to the atmosphere, which is again going to result in higher temperature. At the moment we have 12.7. Let's just increase the speed to reach the kind of equilibrium. So as you can see, now we are in a place that the change is almost plateaued, and therefore this is going to again decrease, meaning that it's going to increase, the absorption is going to increase. As a result of that increase, more thermal energy we are going to have, resulting in less clouds in the sky and more CO2 gases released to the atmosphere. And this scenario will continue. Absorption increases, fewer clouds, more CO2, and it's getting more of that. Fewer clouds, more CO2, and again this is continuing. So we decrease the albedo to increase the amount of the sunlight being absorbed, increase the CO2 because of the global warming, and this will continue like that, which will result in more absorption. So you can see that now we have reached to about 44 degrees of Celsius. Before we were in like 12 in the beginning. And this exponential increase is the exact outcome of having basically feedback loop in the system, in this case a positive feedback loop. Now for whatever reason, if we can intervene and reduce the amount of CO2 gas, we are going to see that temperature is going to drop. As a result of temperature drop, we might have some greenery on Earth growing, which results in lower rate of absorption, which itself is going to contribute to lower thermal energy. Therefore, we might see more clouds in the sky, or even less CO2 in the atmosphere. And you can see this now, this negative feedback loop is taking the system to the previous state it was, and that's how feedback loop contributes to a system's functionality.